The time is up, guys.
Yeah, yeah, are we back?
Is everybody back? Adishwar, Anahat? Anahat, are you there?
Yeah, I'm there.
Okay. So let's begin with the second round, shall we?
Yeah, I'll just share my screen.
Yeah, so that tell me when to start the timer.
Yes, I'll just share this.
Also, Mr. Gyani, did you check all three of our scores have been submitted?
Let me see the spreadsheet. Yeah,
Okay.
all three teachers have submitted.
The current round is dripping faucet, the conundrum 6, right?
Yes.
Yes.
Okay.
So I'll be starting in 3, 2, 1.
Yes.
Hello everyone, I'm Sukada and today we'll be investigating the problem dripping faucet. A leaky faucet develops interesting dripping patterns where the time between the drops depends on the water flow rate. Our task is to investigate this phenomena and study how it depends on relevant parameters. This will be our overall overview. Our main task will be to quantify how interdrop time interval depends on the flow rate, viscosity, pressure, and gravity through dimensionless analysis. This is the legend with all the variables and the units along with their description. We'll be quantifying five main hypotheses here. Let's talk about the first setup that I used. It was a very crude and primary setup, which worked on the continuity equation, which has been stated. We used it to quantify only one hypothesis, which is the interdrop time interval delta t decreases monotonically with increasing flow rate, suggesting an inverse relationship between the two. As you can see, that the setup's diameter has changed from 2.5 centimeters to 0.5 centimeters. The tap's flow rate was manually varied, ranging from isolated droplets to a steady stream. Through the data, we can see that the data clearly supports our hypotheses with a minor variation on the 1.4, 0.31 because of the crudeness of the whole setup. Let's talk about the second setup that I used, which uses an intravenous fluid setup for a much higher accuracy. Here as well, the flow rate was manually adjusted via a clamp. You can see the dimension of the setup given here. This is a measurement protocol. We're talking about how delta T depends on flow rate, viscosity, pressure, and simulated gravity. This is a free body diagram which shows all the forces acting upon our water droplet. These are some assumptions and known parameters. We assume that all of the fluids are perfectly Newtonian with their viscosity is constant. We assume that they have a perfectly laminar flow as well as no transients with them. We assume that all of our fluids are incompressible and have negligible air drag. We also assume constant room conditions, which is 25 degrees centigrade and 1 atm as in standard lab practice. We also disregard any evaporation loss. We assume that the needle has uniform geometry and it has negligible capillary effects as well. We assume that the setup has constant surface tension and that the needle is clean and unobstructed. We also use G's value is 9.81 meter per second square. And we also disregard any electrostatic effects. And the viscosities of honey, milk, sunflower oil, and water are mentioned and will remain constant as well. Let's take a look at the first parameter that we have, which is fluid viscosity. Viscosity mainly refers to a fluid's resistance to flow. In our system, high viscosity means the fluid resists motion more strongly, so it takes longer for a drop to form and detach, which leads us to our second hypothesis, which is that the drop rate is directly proportional to the fluid viscosity. This is our method of demonstration. We can see here from these viscosities, which are taken at Pascal per second, you can see that we get a power regression. Um, the error bars have been shown here because it's not clearly visible in this PPT. We find that as the viscosity increases, the drop rate decreases, meaning drops form less frequently, and it also matches with Hagen-Poiseuille's law, which has been stated here as well. So, in other words, the time interval between the drops is directly proportional to the viscosity for a given setup and the flow condition, which has been stated here. Let's talk about the second parameter that I quantitatively analyzed, which is terminal velocity. Terminal velocity refers to the constant speed a droplet reaches when the downward gravitational force equals the upward drag force, leading to a third hypothesis, which is that the terminal velocity increases as the angle of the needle becomes more vertical, that is, theta approaches 90 degrees, because of the effective component of gravity acting upon the droplet, which is going to increase. This is our method of demonstration, and as you can see, the free body diagram here states the variation with theta at 45 degrees and 90 degrees respectively. Furthermore, we get this data for water, milk, and sunflower oil on these angles. the graph has been stated here, which shows that as the needle increases, the component of gravity acting on the droplet increases in a direct proportional manner. This causes the terminal velocity to increase, which is consistent with our hypothesis. We also see that the two parallel lines at 45 degrees and 90 degrees reflect on how cos theta scales the terminal velocity. The difference in the droplet shows the angle's influence on effective gravity as well, which confirms our theoretical relationship as well. Let's talk about the next parameter, which is pressure. We'll be using Bernoulli's theorem to quantify this. Bernoulli's theorem states that in a streamline flow, the sum of pressure, kinetic, and potential energy per volume remains constant, which means that as the fluid descends, pressure energy converts into kinetic energy, increasing velocity and reducing the static pressure. Here we vary the height of the system using taking in mind that P is rho g h, so we vary h and use different IV we use different IV needles for that. Sorry, we use different IV tubes for that. So in our setup, if we calculate the pressure for a normal system where we take water and standard height, we get the pressure as 14,715 pascals here. Here we come to our fourth hypothesis, which states that as the flow rate Q increases with an increase in the pressure difference, delta P across the IV needle, we use Poiseuille's law for laminar flow through a cylindrical needle, assuming constant fluid viscosity and needle geometry as well. This is the graphical data that we get. As you can see, it should have crossed the origin, but because of the slightly imperfect data and because of all the imperfect setup analysis, we can see that it does not really pass through the origin as well. But we see that there is a linear growth with flow rate compared to the pressure. So we observe that the flow rate Q increases approximately linearly with the hydrostatic pressure delta P, confirming the direct proportionality predicted by Poiseuille's law. Small deviations arise, as I said, due to the fluid viscosity changes and the minor turbulence near the needle tip. But all in all, it does confirm our hypothesis as well. Let's now talk about gravity. Now, I need to mention that this has been stimulated through theoretical calculations only and numerical modeling, not physically altered in the laboratory. This approach allows us to explore the parameter space and predict fluid behavior under different gravitational accelerations, which is relevant for a lot of real-life applications in space, other planets, or centrifuge environments as well. This limitation now means that our experimental validation of these predictions is beyond the scope of the study, and that whatever results we get should be interpreted as theoretical insights only, not direct experimental observations at all. So we're going to use two parameters here, the Bohr number as well as the Stokes law. So derived from the Bohr number analysis, this relation describes the balance of capillary forces in gravity governing the droplet detachment and size, as you can see here. The Stokes law explains the droplet's falling speed, whereas the Bohr number explains the droplet formation size and the timing. So here, as you can see, the Bohr number has been calculated here with delta T as 1.72 with delta T as 1.72. We have also calculated the Stokes number for each case. For example, I have cited it for two cases here at normal G and at G 1.5 G as well. So we can see the two graphs here. For the Bohr number scaling, we see a power regression along the drop interval to the Bohr number. And for the Stokes number variation, we see a linear increase in drop interval to the Stokes number. There are no error bars in this graph because all of this data is only theoretically stimulated and not performed practically. So we come to so with this, we can conclude that the drop formation delta T decreases with increasing gravitational acceleration following a power law behavior. And for the Stokes law quantification, the terminal velocity of droplets decreases linearly with gravitational acceleration, and the linear regression confirms both our hypotheses as well. Let's talk about three miscellaneous factors: the Reynolds number, the Rayleigh-Plateau instability, and the Weber's number. Let's talk about the Reynolds number, which defines the flow regime as to laminar flow or turbulent flow. It connects the viscosity and flow rate from hypothesis number 2 and the Huygens-Poiseuille's law. For my setup, these were the values, and the Reynolds number is roughly between 1 to 10, which validates my second Stokes law assumption hypothesis and states that my flow is in fact laminar. We can calculate the Reynolds number here. And as you can see, it is laminar for both water and milk, but it nearly transitions for oil. Let's come to the Weber's number, which quantifies inertial versus whereas the surface tension forces. It relates to the flow rate Q as well as the droplet breakup, and it has a critical threshold. If it is above 8, it transitions from dripping to jetting. This is the Weber number that I have calculated, and as you can see, it is well below 1, which indicates surface tension dominance over my initial forces as well. Let's now talk about my Rayleigh plateau instability. It governs the jet breakup wavelength and the droplet radius. It also shows my viscous correction on my growth rate omega, which can be calculated using this formula. I haven't really gone into the depth of this, but it does explain the droplet size versus the nozzle diameter hypothesis, which is my first one, and it connects to viscosity and the surface tension. Our sunflower oil trials, which have a higher viscosity, showed suppressed instability elonging my jets. Let's now talk in brief about my chaos theory. Chaos theory basically helps us to understand how small differences in initial conditions can lead to vastly different outcomes in certain nonlinear systems. Even when the underlying rules are deterministic, the behavior can appear random and unpredictable due to extreme sensitivity and starting conditions as well. In the context of our in the context of the quasi-periodicity in our experiment of the dripping faucet, we can see that the data shows a flow rate dependency, a fluid viscosity effect. For example, particularly in the case of oil, which has a very high viscosity, it shows larger drop formation with irregular intervals, which shows the evidence of quasi-periodicity in our experiment as well. Also, at the angle of 45 degrees, the horizontal velocity components introduce minor perturbations deviating from perfect periodicity. Concluding the research, we see that all the 5 hypotheses have been tested. We can say that the experimental data have have validated all of our hypotheses as well. Coming to the source of the scope of further improvement and research, we can use high-speed cameras and automated image analysis to better understand the drop size measurement and the timing. We could systematically increase the flow rate to approach the transition from periodic to chaotic dripping, mapping the bifurcation diagrams and quantifying the unpredictability better. We could investigate fluids with shear dependent viscosity, for example, corn flour and oil. We could also collaborate with facilities that can provide real life altered gravity environments to experimentally validate all of our predictions. We could use CFD to stimulate the entire drop formation and detachment process. We could also study the impact of surfactants or contaminants on surface tension and thus on drop size, interval, and instability. These are some limits of validity. For example, the fluid, if it is not perfectly Newtonian or if it has a variable viscosity, it will contradict our assumptions. If the flow transitions from laminar to turbulent, it will invalidate the Poisson-Stokes laws. The flow rate will become too high, and if it shifts into a continuous jet or spray, it will furthermore break into discrete drop model. And if the needle geometry changes, if the temperature or the pressure deviates significantly from standard conditions, if the capillary, electrostatic, or evaporation effects become significant, if the gravity varies, for example, microgravity and hypergravity, example, furthermore, if the measurement and precision limits becomes less, if it is not very reliable, if the flow is unsteady or transient, and if the incompressibility assumption fails, or my my setup won't be completely valid. These are some sources of error in the precautions. We could assume, we could ensure that the fluid is consistent, we have a steady flow, the height is accurate, the needle is clean, the environment is stable, the timing and the measurement are consistent, the volume is accurate, the flow rate is not variable, and the needle is perfect as well. Thank you so much.
Okay, thank you, Sukada.
I believe I don't have any time left, right? This
Yes,
is, yeah.
yes, you don't. All right, now comes the clarifying questions of the opponent.
Yeah, thank you. I'll just set the 2-minute timer and then I'll start on my first word. By the way, there's a lot of gray noise. Okay, yeah, it's gone. Uh, okay, I'll just start the time on my first word. So I believe, Sukda, you mentioned in your equation F equals to 1 by delta T, that F is the flow rate. However, I was kind of confused because like that's dimensionally wrong because 1 by delta T has like units of 1 by T, which is frequency, and that's not volume per time. So am I correct that you wrote F equals to 1 by T and defined flow rate that way?
Could you mention which slide number this is on so that I could take a look at it?
Yeah, sure. Just give me a second as I did
Yeah.
not mention the slide number while I was writing.
Remember, you guys only have 2 minutes.
All right. Yeah, I believe it's on your slide 11, right? It's in the top right section.
Okay, number 11.
Yeah.
Just a minute. All right. Um, right. I don't believe I've done that. I'm just talking about my measurement protocol in this slide. Let me just share my screen so that it's better visible for you. I'm
All right,
not
yeah.
talking about the formula there, I believe. I'm only talking about my measurement protocol. This is the slide.
Yeah, correct.
Um,
By the way, have you defined flow rate anywhere? Because if it's not here, then
yes, I have here.
all
So
right.
Q is flow rate, and it has been described here.
Oh, all right. Okay, I must be mistaken then.
Yeah.
I'll have to check later. But okay, so that was like my first question. My second question was, I believe in your scope for like further research, you mentioned constructing bifurcation diagrams as something that could be done in the future. But that's kind of like the core to entire like chaos theory, and chaos theory is your presentation. So how can you skip that? Like, how can you treat that as a next step?
I believe the statement chaos theory in the presentation is a little vague because, I mean, I'm not denying the evidence of quasi periodicity and hence, by extension, chaos theory in my research, but I believe that it's not, I mean, it's not the main point of the research. It does exist and it
Okay,
is a
time
part
up.
of my research.
Time up.
It's not the main
Sukada,
point. Yes?
to the time up. Time up.
Sir, can you?
Okay.
Okay.
All right, yeah.
Okay.
I believe I have
Now the
enough.
next.
I have 3 minutes
You
to.
have 3 minutes to prepare. Time
Yeah.
starts now.
All right, I believe it's time, right?
Yeah.
Yes.
Yes.
All right, yeah, I'll just share my screen.
Yeah, tell me when to start.
All
You
right,
have
yeah.
4 minutes to speak, and then you have to invite the discussion for 2 minutes.
Okay, yeah.
Okay, time starts now.
Okay, yeah. So in this report, I'm gonna be assessing Sukhada's project on the dripping faucet as a chaotic system. Briefly, her report covers some chaos theory concepts, experimental design, and the standard research protocol. So, starting off with the biggest issue I had, the first one was that she mentions numbers like Reynolds and Bonds in a presentation, but doesn't really apply them to the depth that is needed for a project like hers. So, for example, um, she cites the Reynolds number to indicate like laminar flow. She says how since the Reynolds number is less than 2000, laminar flow is visible, but she never really calculates laminar Reynolds number for their conditions. And also, I believe she actually calculated the bond number is usually delta rho gl square by gamma, but she uses it to justify some scaling, saying delta t is proportional to g to the power minus 1 by 2, but she doesn't really mention what the length scale or surface tension is, which leaves her usage of Bond's number dimensionally incomplete. After actual non-dimensionalization, we would get the fact that delta t is roughly Bond times O to the power minus 1 by 2, which is basically base time scale, and that's what the report omits. And then I have problems with her usage of chaos theory. So the dripping faucet is actually a classic chaotic system, but the report's treatment is very limited. In fact, upon asking, she says that it's not the main point and that it's part of the presentation. But most systems like the dripping faucets are fundamentally chaos theory systems. Um, for example, in it's established studies like Cahill in 1990 and Coolett 2005, we can see that return maps of successive drip intervals are required, and also stuff like period doubling routes to chaos and bifurcations, uh, all of which all of which's quantifications and graphs are not present in her presentation. To elaborate on this, Cahalan observed actually that as flow rate increases, the sequence of time intervals goes from simple periodic to doubly periodic. And they actually quantified this using the return map, which is basically a fourth order function of the previous interval. Um to show how this is actually possible and not something abstract and doable only with difficult theoretical tools, I would like to show what an actual chaotic map looks like. It's possible to plot this using MATLAB and Python. And then I would like to talk about the strengths and weaknesses of a theoretical grounding in general. Like, first of all, one strength that I found was that she correctly identified that the dripping faucet is a classic chaotic system. And she also introduced chaos concepts like deterministic chaos and the butterfly effect. She also acknowledged the sensitive dependence on initial conditions, which is good for scientific honesty. She also referenced Lorenz's principles. uh, the theoretical weaknesses, I would say, was that a lot of the theoretical treatment was mostly qualitative. For example, I just mentioned how she did not use mathematical models like return maps or period doubling cascades. Her report also missed detailed nonlinear dynamic analysis found in established literature, as I just showed. For data collection, I would say one strength is like the data trends align with physical expectations, with showing relationships between drop timing, flow viscosity, and gravity. But one weakness was that usual statistical details like sample sizes and fit quality that are present in reports was lacking here. So, on literature alignment, one strength was that she.
Adishwaran, I would like to interrupt. It's time to also the for discussion.
All right, let's stop the sharing.
It's time to call for discussion.
Do I ask a question or does Sukda want to go
Yeah,
first?
we will have
Yeah.
discussion. Yeah.
Adishwar, in your opposition, you mentioned that I don't really talk about. I'm sorry. I think my voice is echoing. Can we stop that if it's possible?
Also, Adishwar, you are supposed to conduct the discussion.
Yeah, the questions are
All
supposed to
right.
be from Adishwar.
Okay, yeah, just a second. My
Go
windows are
ahead.
burst.
Yeah.
Well, I'm not sure how to fix it, but okay, I'll just go like this. Okay. So You mentioned how chaos theory is not a part of my biggest question still is you mentioned that chaos theory is not the biggest point of your research report, but as I showed through modern literature, chaos theory tends to be the most fundamental part for chaotic systems, and the dripping faucet is a chaotic system. So I believe you did mention a few terms, and you did mention the transition to quasi periodicity, but I don't think that's encapsulative enough. Like that's not even a return map or a bifurcation diagram. So my first question is, why would you not include this?
While I do acknowledge that dripping faucets are often used to illustrate deterministic chaos, especially in the transition from periodic to chaotic regimes via bifurcations, I still think that the core of the problem is not limited to chaos theory. The problem statement phrasing leaves the investigation completely open ended. It asks for an exploration of the interdrop interval, not explicitly the chaotic dynamics. Therefore, to approach this rigorously, I focus on establishing a deterministic quantitative framework first based on physical principles and dimensionless analysis. And I think so. This is important because this approach allows for controlled prediction of delta t in the periodic regime, which is essential groundwork before any attempt at modeling nonlinear or chaotic behavior. Chaos is inherently sensitive to initial conditions and parameter variations, and without a solid deterministic pathway which has been laid out before, any discussion of chaos in its own point is moot.
Okay, but okay, wait. First, I'll just like to ask you, the research papers that I cited all had chaos theory as its core, and you're saying that chaos theory. I believe you said that the core of this problem is not chaos theory, but any amount, like even a few Google searches would show you that the dripping faucet is one of the most famous classical experimental systems used to demonstrate chaos. Like even historically, I'll just elaborate on its on why I believe chaos theory is core to this problem, since it's kind of confusing. The dripping faucet is actually studied precisely because its transitions from steady to periodic to chaotic dripping as a function of flow rate. In fact, that's something you mentioned as well. So given that this is true, this transition will obviously have to be governed by deterministic nonlinear dynamics. Again, as you said, correct? I believe you mentioned how this transition is governed by deterministic nonlinear dynamics.
I did.
That is the domain of chaos theory. Like if you Google deterministic nonlinear dynamics, that's that's basically um, that's kind of like a subset of chaos theory itself. So what you're using is a subset of chaos theory, and yet you say it's not the core of your problem. So like that's kind of contradictory for me. Could you just explain how you can agree that your transition is governed by deterministic nonlinear dynamics, which is the domain of chaos theory, and at the same time say that your core is not chaos theory?
Alright, I'm gonna have to read the problem statement once for both of
Yeah,
our
sure.
clarifications. A leaky faucet develops interesting dripping patterns, but the time between the drops depends on the water flow rate. Investigate this phenomena and study how it depends on relevant parameters. I'm not saying that chaos theory is not a part of it, of course it is. But before you want to investigate anything chaotic, you first have to lay a basic groundwork or a framework to establish chaos. I mean, of course, it is a very integral part, but I believe that talking about viscosity or talking about pressure or gravity comes first before chaos theory.
Okay, yeah, just a follow-up on that. You just emphasized flow rate, right? When you repeated the problem statement, but you say that chloride is central to the dripping faucet problem, and then claim chaos theory is not core to it, yet also say that we must lay a basic ground to establish chaos. Isn't that your duty as a reporter? You should, if chaos theory really happens after you lay a basic ground to establish chaos, that's your duty, right? You should have done that if you yourself say that it's important to establish a basic ground for chaos. Also, since you mentioned the problem statement itself, I'll just re-emphasize exactly why the problem statement relies on chaos theory as its core. The dependence of drop timing on flow rate it's kind of exactly what leads to chaotic behavior in the system. If your entire investigation revolves around how drop intervals vary with flow rate. Um, the question itself mentions that you have to analyze the flow rate, and flow rate is what leads to chaotic behavior. How can you say that chaotic theory is not central to your analysis? And even if, let's say, I believe you said how it's a part of your analysis, you only define what chaos theory is and its relevance to your problem. You don't even use it as a part. You don't use the mathematical functions that come with chaos theory, like return maps and bifurcation diagrams. So even if you acknowledge that it's a part, you don't treat it as a part. It feels like a footnote to show that you understand what chaos theory is.
Alright, the way I look at this problem, when it says change, I mean, when the problem says where the time between the drops depends on the water flow rate, I think about changing the water flow rate and seeing what effect it has on the time between the drops. Now, I think both of us are looking at it in two different ways. You're talking about the dripping patterns, and I'm trying to vary the drop rate to understand the dripping patterns. So, while I'm not denying the use of chaos theory, I believe that using this research as ground framework, we could perhaps in the future understand it even more deeply. But I still don't think that I should have disregarded all of the parameters that I use right now, and I should have focused only on chaos theory. And I still don't agree with that. I'm sorry.
Okay, do you think drop rate is an independent variable?
Uh, no, that is what the whole point of this was, right? I mean,
Yeah, exactly. So
yeah.
if it isn't an independent variable floating in, like you saying, you say that you're varying drop rate to study dripping patterns, while I'm talking about dripping patterns themselves, I guess. But then the whole point is that dripping patterns emerge as a function of how the drop rate changes, right? So like both are functions of each other. They're not independent. So I think you're trying to draw a subtle distinction by saying that I'm varying the drop rate, that you're varying the drop rate, and I'm talking about dripping patterns, but both are functions of each other. So how can you separate the study of drop rate from the pattern it generates? Like rate and pattern fundamentally are pretty linked together as functions of each other. So yeah, like how can you isolate them? It's
All
not a
right.
distinction,
So
right? They're functions. Yeah.
Of course, they are. What I attempted to do in my study was to quantify how interdrop time interval depends on flow rate, viscosity, pressure, and gravity. I think this is
Could you
something that,
repeat?
right, I'm going to repeat that. My fundamental objective of this research was to quantify how interdrop time interval, delta t, depends on my flow rate, which is q, my viscosity mu, my pressure delta p, and gravity small g through dimensionless analysis. That was my
Okay,
prime
yeah.
objective of the research, yeah.
Yeah, but those are control parameters, and those are the control parameters that determine transitions in dripping behavior from steady to periodic
I'm
to chaotic,
sorry.
right?
Yeah, yeah.
And okay, wait, let's just leave it, I guess. Okay. I'll just go to some more general questions. So, um, you basically rely on measuring like volume collected per number of drops, right, to infer the average drop size.
Yes.
So like given evaporation, splashing, and systematic error exists, did you like consider repeating this measurement at different flow rates to check for consistency,
I did.
not to analyze the pattern itself? You did? Okay.
Yes, yes. Would you like to see the raw data? I mean, if at all.
Yeah, no, I trust you, it's fine.
Okay, okay. Thank you.
uh Wait, how much time is left, by the way?
Yes, time
Sorry.
up. Time up.
Oh, okay.
Okay.
Time up. Okay, now the next part. Next part is 1 minute. Opponent will summarize the discussion in 1 minute. Are you ready, opponent?
Yeah. Okay. Okay. I'll just start the time on my first word. I'll start the timer.
Yeah.
Okay. So Sukada claims that chaos. First of all, I'll give my summary. Sukada claims that chaos theory isn't central to the dripping faucet problem, yet investigates how interdrop time depends on as she said, flow rate, viscosity, pressure, and gravity, the very parameters that govern transitions from steady to chaotic behavior. This contradiction weakens her theoretical framing. She emphasizes drop rate over dripping patterns as an as an objection to chaos theory, but in reality they're not independent. Dripping patterns emerge precisely from how drop rate evolves with flow
है
condition.
मेरे पास, नमकीन दे दो, नमकीन ले आओ,
Adi-
थोड़ा सा मजा आ
She also
जाएगा.
she also
Akshat,
defines.
Akshat, you're
हाँ
mute,
खा
please.
लूंगा.
Yeah, I'm
Akshat,
sorry.
हाँ.
mute.
Damn, that was embarrassing.
Yeah, yeah.
Okay,
All
yeah.
right, Adi should continue. Yeah, sorry.
Yeah, so that was okay. Wait, time's up. But yeah, I'll just add in one more line to compensate for the interruption. So, finally, what I'd just like to say is that she also treated bifurcation diagrams as a next step, which I disagree with because it's a central tool to chaos theory. If you're claiming chaotic behavior happens, she did because he said how her system's behavior is chaotic. A bifurcation diagram isn't just a fancy visualization; it's kind of evidence. Yeah, that's it basically.
Okay, now it's time for the reviewer.
Yeah, so for my questions, I have the first question for the
3
reporter.
minutes. I'll start the
Yeah.
timer now. Yeah, 3 minutes.
Okay, so you mentioned that your system is chaotic. Can you define chaotic behavior?
Alright, just give me a second. So when I talk about chaos theory, I'm talking about how a very small parameter that could seem insignificant significantly varies my results. So that's what I'm talking by a chaotic system where,
So,
yeah,
yeah, so
yeah.
there is a couple more parameters for chaos theory, but we'll go over it. Have you measured have you measured the Lyapunov, I'm sorry if I'm pronouncing it wrong, but the Lyapunov exponent for the system?
No, I would classify it as the next step in my research. I will be doing it in the
But
future,
yeah,
but
so if you
not at this
haven't,
phase.
yeah, so if you haven't actually measured the exponent, how are you defining that your system is chaotic? Isn't that the first step
Um,
you should take if you could try to argue that yes, you have a chaotic system?
no, when I say that I have, when I say that, I'm sorry, my voice is echoing. Can we stop that, please? If it's possible. So, from my
Okay.
data, hello? Right, it's not echoing now. So I can say that my system gets into chaotic theory, and I have an evidence for this because my flow rate dependency shows that at low flow rates, the drops are nearly periodic, and as the flow rate increases, the intervals shorten but exhibit a variability that is in the error range of 0.02 seconds approximately. Furthermore, oil, which has a higher viscosity compared to milk and water, forms larger droplets with irregular intervals compared to water, which has been mentioned on page number 23, where I talk about the Rayleigh plateau instability as well. And thirdly, at 45 degrees, the horizontal velocity components introduce minor perturbations deviating from perfect periodicity. So, based on these three
Uh,
evidences, I can say that my system gets into quasi periodic behavior.
okay. My question, I guess I have to ask the opponent now.
Yeah.
Um, okay. Could I ask two questions to the reporter and then move to the opponent, if that's okay?
Just be fast, okay?
Yeah, okay. Okay, so in your when you were measuring terminal velocity, would you say that the terminal velocity with the changing of the needle is due to a changing in the is due to a change in the gravitational component acting on the water, or due to a change in the air resistance?
As I've mentioned, it's because of the change in g cos theta component. So I'm going to say it's because of the gravity component.
Okay, yeah. As for the reporter, as for the opponent, sorry, do you believe there is no other way to model the parameters that the reporter has explored other than chaos theory?
No, I don't, because all evidence of modern literature shows how chaos theory is used to model parameters. But within chaos theory itself, you can use different models to evaluate the effect of the parameters, like bifurcation diagrams and chaos maps. But you cannot, I don't think you can replace chaos theory itself.
Okay, and finally, so for the
The time is up, I suppose.
could I ask one last
No,
question?
no time.
No, the time is up. Sorry.
Okay. Uh, I have 5 minutes to prepare it.
No.
Yes.
Yeah.
4 minutes actually.
My bad.
Okay, your time starts now.
You have 2 minutes. Reviewer
Oh,
has
sorry, you
2
have 3
minutes.
minutes actually. You have 3 minutes for preparation, okay?
2 minutes. 2 minutes. Reviewer has 2 minutes.
Fine, 2 minutes.
Yeah, so
Be quick.
to use a different method than the one the opponent suggested. While if since the system is extremely chaotic, there probably should have been bigger emphasis on chaos theory. It is completely scientifically sound to use your own statistical methods rather than trying to focus on a specific method of modeling a system. As for the reporter, the main merits of the reporter were that many different parameters have been explored, providing a very holistic view of the phenomenon. There is a very good qualitative explanation of the underlying physics or the equations for the explored parameters. There is also a very relevant qualitative data analysis that shows the trends between the theoretical expectations and the experimental data. And finally, the reporter has done a very good error analysis. What this means is that the reporter was able to provide very good sources of error, both the ones they were able to analyze and the ones they weren't. Along with that, they were able to provide the future improvements that could have been made to the setup to it could have been made to the setup to perhaps reduce these errors. And the reporter has also provided very clear error bars in every single graph to clearly show the uncertainty in this system. However, there were many demerits in the report as well. First of all, there was no clear theoretical model given, and hence no quantitative relation between the theory and the experiments. Uh, in any scientific research, it is very important to have a theoretical model and to have some theoretical predictions that you make that are not just qualitative but quantitative as well, and then show that your experimental data matches these quantitative predictions. Or if it doesn't, then why it doesn't. Having no quantitative predictions at all is a very big flaw in any sort of scientific research. Secondly, even though the qualitative analysis is present in the slides, it's skipped over too briefly and it's not properly explained for every parameter. Perhaps because there was too much and not enough time, the reporter has failed to properly explain every single detail of her of the qualitative explanations. And also it is all of the hypotheses were simply flashed on a slide, and they were not properly explained, and they were not properly set out until after the quantitative data was shown and after the experiment was shown. In any sort of research, I believe that there should be first a very good understanding of what the hypothesis is and why that hypothesis has been created before you move on to showing your quantitative data, which is not done in the reporter's case. Finally, the quantitative data analysis is lacking in certain parameters. For example, in the viscosity versus time interval graphs, there is only a qualitative analysis done that they are directly related, but the proportionality constant is missing. There should be very good quantitative data analysis done of the experiment if you are going to be using if you're just going to be proportional using proportionality and trying to see that direct relation. If you say that it's a direct relation, you should show the proportionality constant as well. Or if it's an inverse relation, show the constant for that as well. That is not present for every single graph. Finally, for the reporter, I believe the reporter slightly misunderstands the terms they're using. More specifically, chaotic behavior. They say the system is chaotic, but for any chaotic system, you obviously have to measure the Lyapunov exponent to prove that the system is chaotic, and also you have to prove that the criteria that were provided by Edward Lorenz are correct. That is, it is sensitive to initial conditions. It must be topologically transitive, and it must have dense periodic orbits. The reporter has proved the first one, but has failed to prove the other two. And also, while the qualitative analysis was always given, they missed out on an opportunity to provide proportionality constants. As for the opponents, there was a good understanding of the problem and the ways it can be analyzed. Oh, sorry.
The time is up, Anahat.
Oh, time is
Sorry.
up. Oh, could I conclude?
Just 30 seconds.
Yeah. As for the opponent, there is a good understanding of the problem, and the opponent does have good research as to how it can be analyzed. But the opponent only focused on a small part of the report and kept trying to argue about being able to use chaos theory and tries to bring in their own methods rather than analyze the ones presented by the reporter. Whenever you're reviewing a scientific research, you are trying to review the research done by the reporter and not trying to bring in your own research and bring in your own methods, but rather try to critique the ones that are already being used and see how they can be improved. So that was a very big flaw in the opponent's discussion. Thank you.
Okay, next is 2 minutes for the reporter to give concluding remarks.
Yes, thank you so much. I'd like to begin by. I'm sorry, my voice is echoing again. Can we do something about that? Yeah.
It's
Now,
fine on our end, actually.
okay. Okay. I hope it's not. Okay. I'll be starting on my count of 3, 2, and 1. Firstly, I'd like to give my final remarks about the chaos theory given by the opposition. I'd like to say that chaos theory applies to irregular aperiodic regimes. My experiment deliberately avoided that by maintaining controlled periodic dripping in an attempt to focus on deterministic relationships. I changed parameters like pressure, viscosity, and orifice size to quantify delta T systematically. Analyzing chaos would have needed a completely different setup. That is, I would have required a long time series, Lyapunov exponents, and precision timing beyond this project scope at this current moment. So no, chaos theory isn't the central thing here, and claiming it misunderstands both my methodology and the physical system as well. Furthermore, I do mention the Reynolds number and the Bond number because I'm using it only to quantify the effect gravity has on my system. Hence, I cannot provide actual experimental data on the Bond's number because it has been used specifically and it has been used superficially on purpose because I do not have the sources to quantify it at this point. Furthermore, I do calculate the Reynolds number on page number 42, which the opponent claims that I did not. Furthermore, I do agree that I could not explain every single thing because of the time limit, as the reviewer said, but I worked in the assumption that since the presentation had been provided beforehand, it was clear itself. So, as for the proportionality constants to the reviewer, the actual laws with the equations have been stated later, relating and hence revealing the proportionality constants later as well. So, I still think that chaos theory is not the most important thing in this. And while it does have a lot of scope, and while I could use it to quantify my results better, I still believe that the current modeling has been done appropriately. Thank you.
All right. Thank you, Sukita. Let's begin with questioning, Mr. Gyani, shall we?
Yeah, let me start with the reporter.
Okay.
So, Sukada, the problem statement, if I read it, it says, once again, the problem statement says, interesting dripping patterns between the time between drops, how it depends on the water flow rate. So what patterns did you observe?
I observed a quasi-periodic dripping pattern in my system.
What do you mean by quasi-periodic?
As in, the flow rate isn't uniform, but it varies slightly, and that is unpredictable.
No, no.
The slight
Pattern is in
variations are
the
not.
flow rate is the dependent variable or independent variable. Water flow
I'm
rate,
sorry.
is water flow rate the independent variable or is it the dependent variable?
It is the dependent variable.
No, if you read the problem statement,
It's the
it
independent
is the
variable, right?
independent variable.
Yes.
Yeah.
And how do you measure water flow rate?
Then I believe the independent and depending analysis has been an error in my fault. As for measuring the flow rate, I have used a 30 frame per second camera to measure it.
What is the unit of flow rate? What is the unit of flow rate?
The unit of flow rate has been given as liters per second, or in some cases, milliliters per second.
What did you use? Liter per second or milliliter per second?
Milliliters per second.
So how will the camera help in measuring milliliter per second?
So as to find out the flow rate, I actually first collected all of the water droplets into a tube and I kept a camera in front of it. Then I slowed down the speed of the video that I got, and then I calculated, and then I manually counted the amount of drops coming. And then with the amount of fluid that I had at the end of per minute, I could calculate the flow rate and the drop rate simultaneously.
Okay. My question for the opponent, in the report, she mentioned that terminal velocity depends on the angle of the tube. Do you agree or disagree? And why?
Um, okay, so
And
first of all,
also one more, and adding on to that question, do you think the water droplets can achieve the terminal velocity?
okay. Uh, to answer the first part of the question, I think the angle of the tube can affect the terminal velocity indirectly by changing the geometry of drop formation. But I don't think it's a direct relation. Although if you look at like low Reynolds number surface tension dominated systems like a faucet, the dominant factors are viscosity and surface tension and like the orifice size, the size of the hole the water is coming out of. So I would say the effect exists, but it's kind of secondary.
Once the droplets are released, they are in free fall, right? All the droplets are in free fall after the release.
Yeah,
So
correct.
how does the angle of the
Your
tube affect
voice
the
cut.
how does it,
Could you just repeat your
okay,
question? Your
I'm
voice
saying,
cut out in the middle.
yeah, yeah. I'm saying once the droplets are released and they have start falling, they are falling in air and it's an identical motion. All the droplets keep falling in air. So how can terminal velocity depend on the angle of the tube? That's an initial parameter. The droplets fall after they lose contact with the tube.
Yeah.
So
Yeah.
whenever they
So
are, how does it affect the terminal velocity of the droplets?
yeah. So yeah, after the droplet detaches, like in the phase, the motion is identical for all droplets if we assume negligible air resistance. Like when I heard the word terminal velocity, I assume that we're talking about the velocity of the droplet just before detachment, while it's like forming at the tip of the tube, which I guess is not a correct interpretation, because at that stage that stage should be governed by like gravity and viscous forces, which can be affected by the angle of the tube. So I guess I understood terminal velocity like differently.
Correct. So do you think terminal velocity is achieved in the system?
Yeah, that's a good question. I would say um, I don't think I don't think like the definition of terminal velocity in this context is appropriate, because when you say terminal velocity, it usually refers to like the constant velocity of an object, like when the forces cancel out, when the force of gravity is balanced by air resistance during free fall. But like for a falling just a few centimeters from a faucet, I don't think there's enough distance or time for it to reach that terminal velocity. For example, in projectile motion, it's a well-known fact that large objects take a lot of time to reach terminal velocity when like released from air. So I don't think in most dripping faucets the droplets achieve terminal velocity in the air.
So, Sukhuda, what do you think about this and your theoretical model, which was based on your this terminal velocity?
Um, I think the way I looked at it was using Stokes' law, which is 2 by 9 viscosity of drop minus the density of drop minus density of air multiplied by gr square upon the viscosity of the fluid. So here I found out that the terminal velocity is directly proportional to g cos theta, and then using that I varied the cos theta component, and in extension.
What are you referring to as terminal velocity? Like, what are you referring to it as? Is
I'm
it
referring.
is it like the general notion of terminal velocity? Because that is only after your droplet has come out of the pipe and has traveled a long distance in air. That's when you achieve terminal velocity. You can't achieve terminal velocity inside the tube or the syringe.
Right.
Or are you referring to that as terminal velocity?
I have referred to the first definition that you gave as terminal velocity, and I agree that it is an error in analysis on my part. I agree with
Okay,
what you said.
Vivek, what are your comments about the fact that the reporter has used gravitational field as stimulated gravitational field? It's like an independent variable. Is it justified or not? Can you use gravitational field G as an independent variable?
Um, yes, I believe we can.
But how can you control G for
Um,
droplets of water?
it
They
is
all are
out.
going to fall after they lose contact with the tube. So they will all fall vertically. So you use G cos theta, but G cos theta is the angle of the tube, but the drops are all falling vertically. So how can you apply G cos theta to the drops?
In that case, I accept that this is a fault in analysis on my part,
Then
and
your
I will.
experiment should have shown a straight line, right? For
Right.
any G, because if you change d cos theta, but the dripping time, the time taken for the droplet to go from the pipe's end to whatever surface you are measuring in, the time should be same for all the drops. Why did you see a pattern there, or why did you see a pattern? Because there shouldn't be any pattern there. It should mostly be a straight line.
Yeah, so the pattern that I saw for terminal velocity versus the needle angle, it is a straight line with three different slope for three different fluids.
Right. So did you miss out on this insight, or
I
that
did.
did
Yeah. I didn't think of
Okay,
it this way.
reviewer,
Yeah.
Anath, question for you. Suggest how Sukuda could have designed her experiment for this problem statement to capture the pattern between the time interval between the successive drops and the flow rate. Suggest a suitable experimental design. Anahat, you
Yeah.
understood my question?
So the question, I'm just trying to think of an experiment design. I guess
Okay.
really just vary the flow rate, like have tubes of multiple different diameters, vary the flow rate, and then use like a video to just record the experiment, and then after it's done, it's just using the video to make sure that that's accurate. Just check the time interval.
How
Okay.
do you define the time interval between drops? How do you define the time interval between drops?
That could just be measured using like either if you're taking a video, then then you look at when one drop happens in the second one and look at the time in between, or if you're doing it live, then you use a stopwatch. I guess that's how you
What
measure
are
it.
the successive events? The formation of the drop or the drop striking a surface?
The drops tracking the surface.
Okay.
May I ask a question to all three of you?
Yeah, sure.
Okay, so
Sure.
during opposition, Adeshwar mentioned about the fact that non-linearity is the subset of chaos, right? Hmm?
Are you asking me?
Yes.
Okay, yeah, I did mention that.
Okay, so Sukita and Anaha, do you agree with this?
I haven't looked enough into chaos theory, so I think I don't know enough to comment on
Okay,
this.
Adeshwar, simple pendulum. Using first principle, if we perform some analysis, we have a well-defined equation for it, right? So is it always simple harmonic?
For simple pendulum, I don't think like it's always simple harmonic because like SHM is
Is it a linear system or non-linear system?
I would say yeah, if you're using the first order. Actually, like technically, I don't think it's a linear system because it's an approximation that holds only like when sine theta is equal to theta, which is when theta is very small. Like if you look at the expression for simple harmonic motion,
Exactly. Okay, I get it. I get the answer. So comparing that to the work presented by Sukada, why do you not think there must be some approximate window, a particular definitive window kind of thing, under the parameter of which the theory which is presented by Sukada will agree?
wait, could you repeat the last part? A particle window, I didn't get it.
A particular window, I mean, just like in the cases of simple pendulum, we approximate the angle to be small enough for the pendulum to be performing simple harmonic oscillations.
Yeah.
Why can't you agree on the fact that uh, using a similar window for the independent variables there are in the Sukada's problem, we can apply similar conventions to this, so that the whole scenario does not become nonlinear, kind of.
Yeah. I mean, yeah, that's actually a pretty good point. Like in most physical systems, we do apply linear approximations, like within certain regimes, especially in simple harmonic motion, and like as you mentioned, small angle pendulums.
Okay,
Uh,
so which one exactly holds true in Sukada's case? That's what my question is.
Yes, I would say in Sukada's case, like the system's behavior is inherently non-linear, which is not the case with simple pendulums. Like even within like small variations in flow rate, as she mentioned, you have non-linearity. I don't think you can approximate it like a physical simple pendulum. Like it's no, like she also said, it's known to be like sensitive. Like it has sensitive dependency to flow rate. So even like tiny changes can shift the system from periodic to chaotic. So, like it's explicitly mentioned that small changes can cause the transition from periodicity to chaotic regimes, which is not the case with the physical pendulum. So, I don't think we can like that. I don't think we can use that analogy in Sukada's case.
Okay, so Sukada mentioned something called quasi-periodicity.
Yeah.
What do you mean by it? What do you understand by it?
Yeah, so I believe she gave some definition based on how it goes from random to periodic to random, but like the definition of quasi-periodic is usually just it's like almost periodic. So it goes from
Is it
uh,
almost periodic or something which appears periodic but it isn't? There is a difference between two. There's a great deal of difference between those two statements.
yeah, so by almost periodic, what I mean is like effective periodicity, you could call it. It looks periodic, but it isn't. Like in physics problems, we have effective mass. I would say, yeah, you raise a fair point. I guess quasi periodicity is kind of like effective randomness. It looks like randomness, but isn't. Yeah, I agree with
Okay,
the
so
definition.
do you think that fact explains the introduction to the system being apparently chaotic? Well,
No, I don't think including only that piece of information is enough to describe its chaoticness. Like as the reviewer also mentioned, you have to include the Lyapunov exponent and
what is
Sukadam.
Lyapunov exponent, by the way?
Okay, yeah, it's a pretty famous exponent in fluid dynamics itself. Um, I don't know exactly how to express it, but it's actually in maths and it characterizes like sorry.
Any questions for the reviewer? Any questions for Anahat?
The same thing for Anahat, I was trying
Yeah.
to ask. Um, Do you think there is a fair bit of correlation between the fact that this phenomena is quasi-periodic and the fact raised by Adishwar that it is chaotic? Uh, what kind of relation holds true within these two
Yeah, so
points?
I guess that would be true. It is quasi-periodic because it is chaotic. But at the same time, I think the reporter really needed to like measure the Lyapunov experiment, which is basically just a measure of how sensitive a dynamical system is to its initial conditions, and prove its chaotic behavior formally like that, instead of just saying that it's quasi-periodic and therefore it must be chaotic.
All right. Thank you, everybody. Good work.
Okay, I think we can conclude stage 2 and take a 5-minute break. Akshat, start the timer. 5 minutes.
All right. See you guys around 5 minutes.
Hello, time is up.